Powerful telescopes are very big and very heavy, and this is a problem here on Earth. There's a limit to how big you can make a telescope, but the problem is even worse when you want to go to space because you have to launch all of that mass into space. And we saw with James Webb at a 6.5 meter primary mirror, it's a lot of telescope. It was sort of the limit what could be launched into space. But to do like the next generation kinds of questions that we have, we need bigger telescopes in space. And so my guest today thinks he has cracked a big part of this question, and that is, what if you could launch very thin, flexible, membrane-based telescopes? These telescopes could be a fraction of a millimeter thick and yet expand out to tens of meters across. But having a membrane-based telescope made of a very thin polymer covered in a mirror is going to be very difficult to work with. And this is the part of this idea that I think is really ingenious, which is that if you heat the back of this membrane very carefully, you can distort it. And you can use that as a way to get the mirror into perfect alignment, even though it's just this sheet of polymer floating in space. And this is a way that you could launch larger and larger space telescopes. And so my guest today is Dr. Sebastian Rabien. He is a scientist at the Max Planck Institute for Extraterrestrial Physics. He is working on this idea of a polymer-based membrane telescope. He's tested this in the lab and demonstrated that you can make the mirror, you can deform it using slight amounts of light and heat, and you can maintain a high level of optical accuracy, and thinks that this will then scale up nicely to go to space. And so imagine a future where 6 20-meter space telescopes are all launched on a single Starship flight. They unroll in space, and now you have an interferometer of 6 telescopes 20 meters across. Blows the mind. And yet this could be feasible if this technology works out. Now, we talk about this idea of the membrane space telescope, but Dr. Rabien's day job is to work with a monster camera on the extremely large telescope. And so we spend a little time talking about that as well. All right, enjoy this conversation with Dr. Sebastian Rabien. Dr. Rabien, thank you so much for taking the time to chat with me today. I saw your paper on Archive and immediately just had to reach out to you and talk to you because it's like a really clever idea. Before we get into your specific paper, you sort of talk about this idea that adaptive optics is sort of the key to modern ground-based telescopes and has applications in space. People are very familiar with adaptive optics and how it works here on the ground. How would adaptive optics work in space? Why is it necessary?
Well, basically, adaptive optics comes always into play if you either have to compensate for very fast variations as you have it on ground from the atmosphere that distorts your phase of the wave that's arriving your telescope. So you have neither fast correction to get a diffraction limited performance of the telescopes. In space, actually, you have other disturbing elements, which is, for example, when you launch your telescope, you have the gravity release. You unpack your telescope, like has been done in the JWST. And let's say JWST has a very rudimentary element of an adaptive optics system on board. So it can adjust the position of the segments, and it even can adjust the local curvature of each segment. So that's, let's say, it's a very lowest order of an adaptive optics system. But even due to that, JWST is so successful since it delivers very sharp images. And there will be the other telescope, which is going up, which has a prototype of an adaptive optics systems on board, which is Nancy Grace telescope. And this as well has let's say, the coronagraph system on board that uses deformable mirrors. So it's coming. And a lot of people in the space business, building telescopes, etc., are working on adaptive optics systems, either to compensate an perfect primary mirror or for other purposes. So that's really, let's say, migrating now a bit from ground to space. So that's
right. And so when you build the telescope, it's under a gravity well. It's inevitably going to have slight distortions,
Yeah.
then it would be great once you're in space and you're in those final conditions. Then you can change it as well as based on any kind of thermal changes that are happening from the sun and so on. That makes a bunch of sense. So let's talk about your idea, this idea of a membrane space telescope. Why don't you give us sort of an overview of what your idea would be?
Yeah. Basically, if we imagine that at some point in time we would like to have a really large telescope in space, yeah, or since thinking maybe of interferometrically combining telescopes, you want a lot of big telescopes in space. Yeah? We need building blocks that are significantly, let's say, simpler, cheaper, and affordable and launchable in a small volume. And let's say this very naturally brings people to the idea, well, can't we, let's say, pack a thin membrane, since it's doing the job of reflecting the light, and could be packed in much smaller volumes than a heavy big glass mirror. And in addition, it brings very, very low aerial weight, which is key, I think, for a large telescope to be brought to space, since any kilogram costs a lot when launching a system. And therefore, a lot of people already have been thinking of why not using a membrane. On the other hand, it's not so simple as one thinks, since everybody who had some membranes, either from kitchen or, let's say, unfolds an aluminum foil somewhere, you see immediately that thin systems tend to not keep the shape, and as well wrinkle and form things that you will not be usable for a telescope. That needs to be precise to the fraction of a wavelength, which is lambda tens is the usual, let's say, rule of thumb that one would like to have to get a good diffraction limited performance. And let's say my invention, or let's say the move here, was to attack two sides. How can one make a membrane that already has a proper shape that you want to have as a primary mirror? And the second key thing is, if you have these flexible membranes that already is maybe half well shaped, how can one bring that into the final good shape? And that's, let's say, the two key elements that we've been attacking here. And second one goes.
So let's talk about the membranes themselves. And you mentioned like aluminum foil. What is sort of the thinking if you wanted something that was large, tens of meters across, but very, very thin? What are the kinds of materials that are feasible today to build a mirror that big?
Yeah, we've especially been looking now into polymers, since polymers are flexible. They can be, depending on the type, can be rolled and be, let's say, and lightweight, and let's say much simpler than any metal foils. And since metal foils tend to deform permanently if you treat them wrong, and let's say some polymers can, let's say, are more tolerant. So let's state it like that. And people have been looking into custom materials and then stretching them over, let's say, a solid mandrel that already has the proper shapes that you want, and then maybe thermoforms then on top of that. That has been tried out. And let's say, I think that's a way possible maybe for smaller mirrors, but at the moment you imagine you want to have something which is beyond a 10-meter aperture. So let's say your solid mandrel is becoming as expansive as a big ground-based telescope, and as well you need to as well shape it properly. So we've been using a trick here, which is very old, and we combined it with another method, which as well is old, but in combination brings us to a method which deposits a polymer onto a rotating liquid mandrel. So we have a liquid in a chamber, and as well as this liquid rotates. And it's a well-known fact that a rotating liquid in a container forms a perfect paraboloid. And to have it perfect, we let's say, shield it from the outside. We put it in a vacuum chamber. you pump the air out, therefore no winds are there, no dust, no dirt, and the liquid is free to form the perfect surface. And so this is just this shape giver, let's say. Yeah? And on top of this liquid surface, we grow then with a chemical vapor deposition process the polymer. This takes a while, yeah? But at the end you can control the growth rate and the thickness of the membrane to the desired one that you want. And this, let's say, after the end of the process, you can release this polymer from the liquid, wash it away, and you have a thin, already pre-shaped membrane that is a perfect paraboloid.
Wow. And then at this point, it requires silvering of some way to make it reflective for the wavelengths that you're looking for.
Yeah. So basically, the polymer we are using is transparent, and you overcoat the front surface with an aluminum or gold or silver, so that it sticks all to the surface. So that depends now on your application. And we've been trying that. It works quite well. And usually now our test units are coated with aluminum such that they reflect the light in the test tower.
And then give us a sense then of, like what is the thickness of this polymer with the aluminum reflection, in a kind of per square meter.
We've been using until now polymers up to 200 microns thickness, which is relatively thick, to compare to standard kitchen stretching foil or something. But this gives us the possibility that this polymer doesn't wrinkle when you roll it, and as well it nicely unrolls when you put it back onto a rest. And so
when you hold it in your hands, what does it kind of feel like? I'm trying to imagine like a piece of rubber, like very, very thin rubber.
It's it feels like a piece of plastic. It's not sticking very well to anything. So it's very low friction material, and but I cannot really tell, since usually I use gloves when touching that thing.
I feel like I'd want to, just find out, but I understand. But so then, per square meter, give us a sense of like what this weighs.
Per square meter, we are below a kilogram in weight.
Right.
So this is far below anything that is, let's say, standard glass mirrors. And let's say, to give you a scale, a 10 meter sized mirror would be approximately 60 kilograms. So two people could lift it without problem.
Right. Compared to tons and tons for a glass.
Of a standard glass mirror.
Yeah. Okay, so this is kind of half of it. And so I guess, with this polymer, you are getting something that is naturally, in its natural state, it wants to be the right shape of a parabola. It is sort of, and that way I sort of imagine, if you had something that was, say, made flat, then if you tried to move it into the parabolic shape, you're going to get kinks and creases, and it's just not going to be the right topology. But in this case, its natural state is to be in this in this parabolic shape.
It naturally forms the parabolic shape that I want to have. And as well, this gives us, let's say, ingredients for the next step. Since the shape is good enough such that I can measure it optically, that I can see the surface. Since if you're, let's say, millimeters off from the desired shape, you have a hard time to measure anything optically, since, let's say, this distorts everything. But let's say in our test units, we are usually in the range of, you see a peak to valley maybe of 10 microns, which is an RMS of approximately 2 for a 30 centimeter test unit. But this is, let's say, easily then still measurable by a standard. For example, we use a Sheck-Hartmann sensor to sense the wavefront. And then you can see the wavefront of the reflected one. And this is, let's say, then the third step. If I can see it, I can do something, I can correct it.
Right. Yeah. Right. But you can't, I guess, take a laser, examine the quality of the surface, and go in with and fine polish bits and pieces that aren't perfectly aligned. Like you're stuck with the shape of the polymer.
Yeah, let's say our polymer itself, it comes off the process in a very good shape. But at the first moment, I pull it off, I touch it, then or put it onto a rest somewhere, which it has some 5 microns or whatever, which is not a bad surface, but it's not optically good. And then it picks up, for example, an astigmatic distortion of the 10 microns plus some bumps left and right, and those need to go away. And then this is then the next step where the adaptive optic comes into play. And looking at the surface, measuring it, and then you need a mean, let's say, to deform the surface, and best without directly touching it, since the polymer is thin and sensitive. And this is a method that we have developed, which is very different from any other actuation that has been done before. We irradiate light onto the surface with that I can locally control the intensity of the light, which basically warms then locally left or right or where I want to warm it. And this slight warming causes then the surface to deform by using basically the CTE, the thermal expansion of the material. And this gives me a mean at hand, which is really, we've found now that it's really great. It works really good. And I have a mean to not touch the surface. I can build this radiative actuation system in a small box, let's say bigger shoebox or something, and it still could actuate a 10-meter sized mirror with a lot of actuators.
And so does you're using light to heat up a little bit of the polymer, and that is just distorting its shape just enough to bring it back into optical alignment to give you that perfect wavefront. And you say a small box. Is it you're still having to sort of have the emitter very close to the polymer, or is it sort of able to the small boxes can affect the entire area?
The small box can affect the entire area. So let's say in a final setup, one would be some 10 meter away from the 10 meter sized mirror, and the small box would sit there and then illuminate the whole surface. You can tailor the objective which is in front of it such that it matches. And you can, let's say, adjust the power of the light source as you want to do that. So, and this could come in 2 flavors. One is using commercial DLPs, so digital light projector, or a laser scanning system could do the same job as well, very easily. And until now, we've been using DLPs, which turned out to be very successful.
So then I guess sort of explain the setup then. So you've got on the, say you have the polymer, you have the emitter on the one side that is firing. I'm assuming then on the other side, you are sort of measuring the shape of the wave fronts that are coming off this telescope, and then knowing how, and then sort of feeding it back to itself So
that's basically the closed loop system that you need, a real-time system that is capable of measuring the reflected wavefront from the mirror. And in a telescope setup, you would look at your object, your star, your planet, whatever you want to look at, and you use this point source as the probe of your mirror. That's how we do adaptive optic as well on the ground. And the starlight is reflected off the mirrors and ends up, let's say, in front of your scientific instrument. And you pick a bit of that starlight and you feed it into a wavefront sensor, such that you can see how distorted is your wavefront. And then you have the computer-controlled feedback loop that then designs, let's say, we would call it modes of deformation that are necessary to bring back the shape to the desired one. Since even in space, I think you would have a variable environment. You change pointing of your telescope. You may have, let's say, bit background radiation if you're close to Earth. If you go to L2, might be better, let's say, there's always some, let's say, even pointing would change, let's say, the shape of the mirror. So you need to actively keep it all the time.
So, I mean, before we talk about space, I would just love to sort of talk about what applications you see here, even on Earth, under the Earth's gravity well. Do you think there's a place where these could be used as telescopes here on Earth compared to these, as we talked about, these multi-ton primary mirrors built for these big astronomical telescopes? I mean, this sounds like a very quick way to get a good telescope operating.
Yeah, we thought about that, and at the moment I would consider it difficult, but maybe it's not thought through yet. The one thing is that these membranes are sensitive. So if you would, let's say, pull it out during nighttime and put it on a mountaintop, it would see winds, would see thermal changes and distort. And if one finds a way to keep winds and let's say thermal changes away, then this could be a viable option. Or let's say where we are not at the end is, let's say, since we're using adaptive optics to keep it in shape, we may find a way to make the response faster. Since currently the radiative, let's say, actuation is relatively slow. So let's say a wind which blows over it could not be corrected. But we may find ways to add on an electrostatic or similar fast response unit.
That's interesting. Is there any kind of wearing down of the membrane as you are, heating it and letting it cool?
We've not seen anything like that. The material itself is a extremely stable, let's say, material. You can use it down to cryogenic temperatures, so minus 200 degrees, no problem. Celsius, sorry. And let's say up to 200 even, so it can be warm and cold. So it's, let's say, there's a transition in all these polymer materials, which is called glass transition. And normally you would not like to store these things above it, which is 50-ish degrees Celsius. Since then you might pick up permanent, let's say, distortions, which don't go away anymore.
Right. Yeah. I can think about plastic that I put in my dishwasher that won't ever be the same again, just because I put it too close to the heating element. It got hit by too hot water. I've sort of learned the places in the dishwasher to put the plastic so that it doesn't completely melt. All right. Now the fun part. Let's talk about going to space. So how do you sort of envision this working as a space telescope?
Well, if it's a single telescope, one could build up, let's say, a package where these mirrors are stored, rolled. And let's say there's a whole structure as well that needs to go with it, which holds, for example, a secondary mirror or the instrument behind the main mirror as well needs to be stored in the same volume. We've made some sketches. There will be several ways of how to, let's say, fold or unfold these structures. But it looks like to me that there's good ways in let's say, folding these structures away and building the roll beside of it. And to me, this looks like that, let's say, even if we are able to roll a 20-meter sized telescope to the tenth of its diameter, which is 2 meters, and this would bring us to the possibility to pack in a Starship now, or in the new SLS, large cargo. We could store 6 telescopes maybe for launch. And so this, to my opinion, would bring an extra possibility here to bring us towards the desired array of telescopes. That brings us a resolution to look at very special objects.
Right. Yeah. Six 20-meter telescopes acting as an interferometer would be interesting. To say the least.
Would bring us to the point where we could think of resolving planets.
Mm-hmm. Yeah.
Planets. Could see weather. or
I
light
mean, that
size.
sounds amazing. But sort of give me an idea kind of practically. So, have you got some kind of rigid ring that sort of holds the outside of the polymer telescope, and then is the emitter connected? Is it free floating? The instruments? I'm trying to sort of
Yeah,
imagine what this will
we've
look like.
developed now one or two schemes how to, let's say, fix this grown mirror to a structure. It looks like that could be relatively successful to just do it with wires or a thin other membrane that you attach to the outer ring. Best in some scheme where you keep it force free after the growth, and then you pull it at 3 points back into the shape. So it's nicely 3 points form a plane, and if you go back into the plane where the mirror has been grown, you would be able to, let's say, get it back. This needs a bit of structure around, but the structure could be very lightweight, and we would be able, let's say, if you do wire pulling, this has been done already in space, and let's say this as well gives you the possibility to control the force finally that you put on the outer ring.
And I know people have been thinking about like rotating structures using that outward centripetal force as a way to maintain the structure of a telescope as well.
One could do that, yeah. That would be a possibility to keep the rotation. It's maybe another degree of freedom that your spacecraft needs to be able to do. That since you're doing as well pointing, and if you have the rotation in addition, it may be conflicting. But there, I'm not a good flight dynamics person. No, that's But it would be physically perfectly possible to do that.
Yeah. Okay. So I'm sort of envisioning you've got this 20-meter telescope, and it's 5 friends that are in orbit. Where do you think would be the best place to put them?
Well, currently, if you're looking for a quiet place in space, L2 is a fantastic location. What you need is a good sun shield to keep, let's say, the radiation away, since it's quite some power which is arriving there. And on the other hand, let's say orbits closer to Earth have the nice possibilities that one could do repair missions or similar. Since to L2, people are thinking of it to do repair missions, but it's much more complicated, I guess.
And we think about these telescopes, like now current telescopes. I mean, James Webb was built with a 10-year lifespan. It'll probably last longer thanks to the very careful launch. Do you see this lasting a shorter amount of time, a longer amount of time than other telescopes that are more made of hardware?
I don't think so. That, let's say, thin polymer has one nice possibility that I think it would be relatively has no problems with space debris. You get a little hole. What? If let's say
punch a little hole right through.
You have a big area, but let's say if you have metal mirrors or big glass mirrors and it's hit by a fast particle, as it may heavily damage it. But of course, there are other parts of spacecraft that can be hit always. And let's say the materials themselves would be good. They're very long-lasting materials, and I think there's a total spacecraft, which normally is designed for such a lifespan that we try to keep it long, but you don't know. There's a lot of pieces in.
I mean, you talk about that idea of the need of a sun shield. That's theoretically then a second polymer probably that would be launched to go with it. But I mean, you're sort of dealing with those temperature extremes. If you leave it in full sunlight, then you're looking at something that sounds like it's probably getting close to the hottest temperature the polymer is comfortable with. But if you do put it into a sun shield, now you're going the opposite direction. You're going to approach, few tens of degrees above absolute zero, like what we're seeing with James Webb. Is there a temperature regime that you would feel most comfortable with this being in?
Well, in very general, if you would build such a telescope, it would look over a broad wavelength regime from best optical, a bit quite in the infrared. And if you go to the infrared, you anyway want to have a cold telescope. So cold telescope is good for astronomy. And since we are actively controlling the surface with heating the materials, we would control the temperature of the mirror. So let's say you could set it to 100 Kelvin, 120 Kelvin, which could be a good regime, let's say, for even to the nicely into the 10 micron regime of observations. And, so let's say we would be passively cooling, but we would be actively heating it to a desired temperature. So that's a design criteria.
Right. That's interesting that essentially the device that you're using to warp the telescope could also be used to keep it warm to whatever is the temperature you're looking for.
Yeah.
So let's talk about pointing. I mean, when you think about a traditional telescope, it's running reaction wheels inside, it's quickly turning, it's got gyroscopes that are keeping it on target. How would you point it?
Yeah, you would use the normal methods that are used in spacecraft to point it. And I think a good move would be if the structure, which is holding the whole thing around it, which is holding the secondary mirror and the instrument, is sort of stiff and not too sloppy. Since, let's say, to avoid wobble modes, they die out very slow. But let's say that you can rotate the whole entity in one unit. And the membrane itself, due to its lightweight structure, I think is a plus for pointing operations, since it comes with the whole structure around it, and then the lightweight membranes will follow it. And,
I see. So if it's only, say, a few 100 kilograms or maybe 1,000 kilograms, that's quicker and easier to move, requires less reaction wheels to move it than something that is
lost reaction forces for the whole thing, and then maybe 20 meters and could be pointed like a smaller telescope as well.
Oh, good. Okay. All right. So it's still going to be fast to point at new targets or track targets that are moving and so on.
This is usually a design work, which is done when you design your spacecrafts and structure, etc. That you look at ion modes and frequencies. That the whole thing is not, let's say, wobbling for hours after you've done an operation.
So let's talk about like a practical next step then. So, I mean, you have demonstrated in the lab all of the key parts that you think make this a viable concept. What would be the next step to sort of show if this is, a possible future space telescope?
Next steps would be a bit at the moment looking for partners that would be interested in continuing that or even commercialize the whole story. And this is ongoing. I've been talking to people, going to conferences, and that let's say that natural thing now to do. I would love to enlarge to the next step to grow a meter 20 sized unit, since you could learn a lot from that. What are really the surface structure functions that you have to deal with on a larger mirror, which would then be more, let's say, representative for going to a big telescope. So there's things to do, and
I've got a couple of questions from our audience. I'll let people know that we would be talking today. Alexander Gross asks, would the time to develop and build such a telescope differ compared to a conventional space telescope?
I'm pretty sure that it could be shortened, since if you build up the machinery to grow these mirrors at your desired size, you can make many, since the machinery is then at the end sort of industrial production of these membrane mirrors. You could grow many. That helps a lot in the development if you can do it.
I mean, we think about, say, the work on the extremely large telescope, which we're going to talk about in a second because that's your day job. But a lot of these mirror segments have taken, in some cases, a decade in the mirror lab to go through the entire process from putting in all the glass to doing the polishing to finally delivering it to its final place.
Yeah, and it's a lot of segments, but actually ESO and the companies that are doing the job for the mirrors are on good path. It's not bad. Huh? It's a whole production facility. I don't want to tell now dates since I don't have it directly here in my head. And they've been doing a good job for the 800 segments which are on the way.
Right. Well, no, and I report on the work that's being done at the Mirror Lab in the University of Arizona, the one that contributed to they make these 8-meter.
Yeah, they did the ones for the LBT and the ones for the Synoptic Large Survey Telescope, which is coming up now. And
and it is about like a 10-ish year process, or a little bit less, for them to go from when they melt all the glass to when they finally deliver that final mirror on the top of the mountain. It's a long process. They've been doing the LBT ones, took a long time, and same thing as you say with Vera Rubin. It's been a lot of work. Mile Milkovsky asks, can various natural lasers that emit visible light or other wavelengths of light coming from the universe cause some change to the shape of the membrane?
Basically not. Yeah? I would need to recalculate what if you point to one of the brightest stars on the sky, how much power you have, but per square meter, that's not a lot. So that's
right.
In general, the universe is full of light, but it is still dark.
Right. Yeah, of course. All right. I'd like to shift gears then and talk about, like I mentioned, your day job, which is that you're working on the camera system for the extremely large telescope. So can you give us a background of this?
Oh yeah, if you want to cover that in addition, so it's let's say my day job. The camera is called Mikado, and it's going to be the first light camera that will be sitting on the NASMIS platform of the extremely large telescope. At the moment, the telescope is ready. So both units are currently being built. So the telescope is growing every day in the Atacama Desert. There's a webcam, actually. One can look at the daily progress, which is fantastic. It's getting really huge, a huge building. And we here at our institute, we have the PI Institute of the Mikado camera, which is an infrared camera that are going to attach to the extremely large telescope. And talking about camera, I told you before that infrared camera needs a cryostat, needs to be cooled down to liquid nitrogen temperatures. And let's say the arrangement at the telescope plus all facilities you need for this infrared camera makes it an 18-ton heavy unit, which is a 6-meter high. And,
right. It's a building, not a camera.
It's a small building, but it's full of technology from bottom to top.
Right. And so when you think about the ELT is going to have this 39-meter aperture, it's going to be collecting all of this light, and then light is going to be bouncing off the secondary mirror. And then is this like the main instrument that's going to be gathering up that light, the main camera, or will there be sort of multiple cameras?
So there will be multiple systems at the telescope, of course. Ours is a near-infrared imager and some spectroscopy. And but there will be a camera with an IFU, and there will be a mid-infrared instrument as well, spectroscopy and imaging, and then others are in the queue. Since, of course, the largest telescope of the world is, let's say, it needs to have quite some capabilities, since it will be serving a large community of astronomers that are all need different wavelengths regimes to observe.
Right. And give people a sense then, like what are the kinds of astronomical objects that this will be ideal for observing?
Can pull here, of course, one out of the pocket immediately, which is a black hole at the galactic center. This is one of our main topics here in our group. And let's say this camera with the 40-meter resolution of the telescope will be capable of resolving tiny objects close to the black hole, so smaller stars. And this will gives an hand of constraining, let's say, general relativity in the vicinity of the heavy black hole.
Right. I think about there was a Nobel Prize awarded for the observations made around the center of the Milky Way and these stars that are moving. And that was all done with, I think at the time, the European Southern Observatory's Very Large Telescope, or even earlier models, and using that infrared capability to look through the gas and the dust to be able to see those stars moving on elliptical orbits around nothing.
Yeah, that looks fantastic. If you look at the movies which we made of that, you can see really stars which are 100 solar masses, and they're moving on orbit. That's fantastic. And from that, of course, you can then measure a lot of things, do a lot of physics. And then the measurements mostly have been done in the early times with adaptive optics at the 8-meter VLT telescopes. And later on with the interferometer and an instrument called Gravity as well. We have been involved here in the PI Institute. And with the interferometer, you get a fantastic resolution. We have a 100-meter baseline there. And so you can see, let's say, stars move to a super high precision. And this gives you a hand on, let's say, the general relativity effects you're seeing there.
And where's the camera now? Is it in Atacama, or is it still at your facility getting wrapped up?
The VLT facility is still there. It will exist there for a long time.
No, the new one. The new one that you're working on. Yeah.
We're building it up. Currently, we're building Mikado up, and pieces arriving in our integration hall here and being put together. And we are then hopefully in time ready with the whole system. So it's a big partnership say with. There's partners all over Europe as well, and they're delivering pieces to us. We are building pieces up, like mechanisms. The cryostat hopefully will arrive soon, and all that needs to be put together, be tested, and at the end, let's say.
Yeah.
Then,
and I guess you're waiting on ESO for when you're going to know your first light.
It's telescope must be ready, and then we must be ready. So of course they're scheduled all around, and let's say latest one can be seen on the ESO web pages. But let's say it's not so far in the future. Let's say within 4 or 5 years we're gonna be there.
Yeah, that'll be great. I mean, it's such a dramatic step up from any other telescope that exists. It's kind of mind-blowing how much bigger this telescope is going to be than anything else. And when you have the adaptive optics, then it makes it feel as if it's almost in space. And I think a lot of right now everyone talks about James Webb, but that's the telescope that will then take. I mean, it can't see the same wavelengths as James Webb, but just the size and sensitivity of this telescope is going to be mind-blowing.
So basically, it's a resolution. It's a 40-meter size resolution that will, let's say, resolve a lot of questions that we have. James Webb is extremely sensitive. This 40-meter and Mikado will reach similar sensitivities in certain wavelength bands. Not at the long end, since of course the atmosphere is killing you. But let's say in the near infrared wave bands where we design for, let's say the 40-meter is as sensitive as a JWST out on L2.
Yeah. Fantastic. Well, Dr. Rabien, thank you so much for taking the time to chat with me today. Good luck with launching 6 20-meter space telescopes in a Starship. That sounds great. I can't wait.
Okay. Many thanks to you, and have a great day.
I hope you enjoyed that conversation with Dr. Rabien. I'm going to give you some references to other conversations we've had that are similar here on the channel. But first, I'd like to thank our patrons. Thanks to Abe Kingston, Adam Schaefer, Barry Lake Roofing, David Giltonen, David Matz, Dennis Alberti, Dustin Cable, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Paul Rohrbach, ScienceWorldRecord.org, Spiderswap.io, Stephen Krasaki, Stephen Fowler-Munley, and Vlad Shiplin, who support us at the Master of the Universe level, and all of our other supporters on Patreon. Obviously, I'm very excited about practical ideas to build larger and larger space telescopes. I mean, Webb is fine, whatever comes with Habitable World Observatory, that's great, but I think we really want to have larger and larger telescopes. So I'm going to give you a couple of links to various interviews that I've done in the past. One is this idea of the solar gravitational lens, that what if you could use the sun itself as the focusing part of a really powerful space telescope. And this is a conversation that I've had with Dr. Slava Turushev. He is the originator of the idea, and we have a really in-depth conversation about how the solar gravitational lens would work, and then a follow-on conversation about how we could get out to the solar gravitational lens in a short amount of time. The other conversation that I think you'll find really interesting is about the Nautilus space telescope. And this is an idea of launching flexible telescopes that would work in a large configuration. You could launch them sort of flattened, and then they would inflate once they're in space and act like telescopes working together or an interferometer. Sort of similar idea, but sort of a different substrate. So definitely check out that interview as well. All right, I hope you enjoyed this conversation, and we'll see you next time.